Welcome to the module on Introduction to Coiled Tubing Applications. Let us begin by understanding the role of coiled tubing in conveying fluids. The most common use for coiled tubing is as a conveyance method for fluids. This encompasses nitrogen kickoffs, wellbore cleanouts, cementing through coiled tubing, acidizing through coiled tubing, scale and paraffin removal. What is nitrogen kickoff? It implies inducing well to flow by lowering hydrostatic head through pumping nitrogen gas. The system is optimum when coiled tubing is at deepest point in well, nitrogen rate is lowest, annulus allows for maximum flow. When wells fail to flow on reopening, they may be lifted back into production by the circulation of nitrogen at depth through such coiled tubing applications. Historically, this operation has been performed using slickline or swabbing techniques. Coiled tubing offers the following advantages: faster and continuous process. Less likelihood of fishing requirements such as swab cups, wireline breakage etc., greater degree of well control. Moving to wellbore cleanouts. It involves removal of fill from wellbore to restore production. Allow for tool passage. Allow for completion devices operation. System is sensitive to fluid viscosity, fluid velocity, wellbore deviation, bottom hole pressure. An important consideration in fill cleanout operations is the well configuration and calculation of fluid velocity at every restriction to prevent serious abrasive damage. This and the fluid carrying capabilities/dynamics are best modeled on a computer simulation to ensure optimum job planning. In broad terms, cleanouts are divided into two categories: removing solids, formation sand, frac sand etc., removing sludge. The removal of sludge is generally best accomplished by breaking up and dispersing the sludge through the combined action of chemicals, surfactants and solvents and vigorous mechanical agitation achieved by high-pressure jetting. The resulting liquid dispersion can then be readily circulated out of the well. Solid fill, however, is substantially heavier than the typical fluids which are currently available for well servicing. As a result, the mechanics of particle transport determine the method of fill removal. There are several different coiled tubing cleanout techniques available, each having distinct advantages for specific well conditions. Each cleanout technique relies on generating circulation conditions in which the circulated media develops optimum transport characteristics for the fill material present. In vertical wells with high pressures, cleanouts are readily performed simply by running the work string into the fill while pumping water. With a flow in the annulus carrying the fill to surface, the particle transport velocity can be determined as a function of Stokes' law. For most fill types encountered, the fluid velocity is designed to be at least twice the particle fall rate. When required, viscosity-enhancing agents such as gelants can be used to achieve this ratio. When pressure conditions in the wellbore are too low to support the annular flow conditions created by the cleanout, introducing nitrogen or foam into the fluid lift medium to reduce hydrostatic pressure becomes necessary. Good quality foam, 75% or better, has excellent fill carrying capability but suffers from two disadvantages. Foam generates significant flow friction, making cleanout operations slow and inefficient when used in small annuli. High costs associated with handling and breakdown of the foam returns at surface. Alternatively, nitrogen pumped in stages, slugs, will reduce hydrostatic pressures for cleanout operations. If proportioned properly, the same hydrostatic pressure reduction can be realized as for foam cleanouts. The advantage is that high flow friction resulting from the shearing of stable foam will not be encountered and returns to surface are more easily handled. Fill cleanouts in deviated profiles require a completely different approach to be successful. The coiled tubing and particles will be lying on the low side and the fluid velocity in the area will be relatively stagnant. Once deposited on the stagnant side of the hole, neither high viscosity fluids, gels nor foam can develop enough turbulence to re-establish particle transport. A secondary problem with foam is that some liquid will also break out of the foam, fluidizing the settled particle bed and causing it to run down the wellbore. The simplest way to remove this settled fill layer is to generate extreme turbulence within the carrying fluid so that the fill can be picked up and moved further up the hole. Water, having a low viscosity, is more easily made sufficiently turbulent such that moderate size fill can be successfully cleaned out of deviated wells. In larger diameter completions, water or nitrogen slugs may be required to achieve the required annular velocity. In exceptional cases it may be necessary to flow the well and use the production commingled with the cleanout fluid to achieve the required critical velocity. However, the safety and surface treatment implications of this technique need to be fully evaluated. Next, let's talk about cementing through coiled tubing. Selectively place cement in the wellbore or in the perforations to pee into well or zone, squeeze off water or gas, and sidetrack. System should be designed for the optimum viscosity, fluid loss, placement. Coiled tubing may be used to carry out cement jobs, such as squeeze cementing. This involves cement being precisely spotted at the perforations. Additional pressure is then applied to dehydrate the cement slurry within the perforation tunnels in order to isolate selected perforated zones. Generally, this technique is not particularly successful for perforation isolation. Cement plugs. This involves the placement of a column of cement within the production casing to isolate the lower section from above. The minimum slurry volume to be placed, which would form an effective plug downhole, will depend on the casing ID. Generally, 0.75 barrel is accepted as the minimum quantity that can be pumped. For such small jobs, use of displacement plugs is essential. To provide a platform on which the cement rests until it sets, bridge plugs, high-viscosity gel pills or sand is commonly used. Assuming that the maximum working pressure of the coiled tubing is not exceeded, there is no limit to the quantity of slurry which can be pumped through coiled tubing. However, there are other limiting factors which must be considered, that is pressure or stress limitations and friction considerations. The design of a coiled tubing cement job is no different from any other, notwithstanding the coiled tubing fatigue and dynamics limitations. Next, let us learn about acidizing through coiled tubing. It involves selectively placing acid in the perforation tunnels or matrix. The process is sensitive to length of interval, which determines diversion technique, pump rate, which is a function of the coiled tubing size, temperature, flowback or cleanup technique. Coiled tubing may be used to spot hydrochloric acid or other fluids to dissolve scale, such as calcium carbonate. The scale is generally deposited in high water cut wells and is normally found where pressure drop occurs, such as the subsurface safety valve and other restrictions. Other techniques, such as the use of coiled tubing with jet nozzles or milling tools and placement of acid with wireline run dump bailers, are viable alternatives to acid washing. It may be employed to spot an acid treatment over the perforations, from where it can be squeezed into the formation. Coiled tubing is used in acid washing or stimulation operations for several reasons, such as spotting the treatment fluid across the perforations is more effective than bullheading large quantities of fluids. Spotting avoids squeezing potentially contaminating wellbore fluids and tubing solids into the formation. Allows complete coverage of the producing interval, although it does not ensure uniform injection, by moving the coiled tubing while spotting the fluid. Reduces the well conduit exposure to the acid, which is important for some exotic or chrome tubulars. Accurate and controlled placement of treating fluid can be performed with the use of straddle packer tools. Permits jet washing to remove superficial scale. By using high nozzle jetting energy and cycling over the target zone, contact with the scale material can be maximized. The technique of underbalanced acid washing is sometimes proposed. It involves the circulation under conditions designed to ensure a positive drawdown of the formation while washing to assist in the removal of damaging fines. However, this begs the question as to whether the acid then actually enters the formation as intended on a localized basis, directly adjacent to the coiled tubing nozzles. Particular attention should be given to planning the corrosion inhibitor schedule for acidizing treatments. Most inhibitor schedules have been developed for standard concentrations of regular acids in contact with regular steel tubulars. New types of chrome and duplex steels are more prone to acid attack, which has prompted the development of completely new inhibitor/intensifier packages. Further, let's read about scale or paraffin removal. It implies selective chemical treatment to restore production, allow for tool passage. It must be noted that the type of scale or paraffin determines treatment type. Hard scale requires mechanical removal method. Conveying tools. The use of coiled tubing to convey mechanical tools have become more and more popular. Washing subs. Check valves for well control. Fishing. Slickline. Downhole motors. HP jetting. Prepacked GP screens. Bridge plugs. Inflatable packers. A method and apparatus for testing a multi-zone reservoir while reservoir fluids are flowing from within the wellbore. The method and apparatus enable isolation and testing of individual zones without the need to pull production tubing. Moving on to fishing, this involves retrieving lost tools or components from the wellbore through tubing. Alternative to wireline fishing or with snubbing unit. Fishing tools and techniques are determined by tough inside tubing or encasing. Fishing neck available, type of fish, stuck, well conditions and geometry. Tools have been developed which have significantly increased the use of coiled tubing for fishing operations. There are a large number of different types of spears, overshots, meals, guide shoes etc., now available. The technique for running them requires experience with the tools and also the way the coil tubing and injector head behave. Precise control of the injector, low stuffing box friction and good weight indicator performance are all factors which can influence the outcome of a fishing operation. Equipped with jarring tools and percussion equipment, high pulling and pushing forces can be developed to free objects downhole. Combined with the ability to circulate fill from the hole, deliver acid or rotate with hydraulic indexing tools, a number of techniques can be performed which are not available with conventional wireline fishing. Slickline. Coiled tubing are used to convey slickline tools or to operate downhole devices. Its advantages include set-down weight, full-bore tools to allow for circulating, superior overpull, up-jarring using hydraulic jars. The ability of coiled tubing to be snubbed into the well provides it with a horizontal reach capability. Jobs normally performed by wireline and vertical wells, such as moving sliding sleeves, need to be performed using coiled tubing in horizontal, long reach and highly deviated wells. For such applications careful consideration needs to be given to the coiled tubing buckling tendencies. Additionally, development work is ongoing with downhole traction systems to overcome the coiled tubing push limitations. Next, we shall understand downhole motors. It involves mechanical removal of hard fill or cement. Process is sensitive to temperature, flow rate, rate of penetration, wellbore configuration. The operation uses a coiled tubing to which a downhole motor coupled with a bit is attached. This is used to break up downhole deposits such as scale or cement, or to mill out an obstruction or side window within the completion. When planning this type of operation, the type of bit and motor required significantly affect the efficiency of the task to be performed. High-pressure jetting. It implies use jetting energy to remove scale by creating a pressure drop across a DH jetting nozzle. Used with hard scale, used with ID variety, nozzles need to cover 360 degree of ID by rotating head or indexing. The process is sensitive to fluid viscosity, rate of penetration, pressure drop. High-pressure water jetting is well established in general industry for cutting, cleaning and surface preparation. Water jetting operations, or hydroblasting as it is sometimes known, is also being applied downhole where the precise control required to maintain optimum jetting conditions is much more difficult to achieve. A significant factor of consideration in the use of HP jetting is the effect that the pressure has on the life of the coil of tubing. A variety of factors influence the effectiveness of a water jet, with pressure being the most significant. However, since the coiled tubing operating life is shortened significantly by higher operating pressures, it is generally not economically viable to use jetting nozzle pressure drops much above 2,500 pounds per square inch. As with any fluid delivery system, there is a trade-off between pressure and the volume flow rate available to the tool. Jetting tools which employ high pressure drops at the expense of volume flow rate, usually very small nozzle diameters, are less effective than a more balanced combination. Similarly, high volume flow rates achieved at the expense of jet pressure are not very effective. Tensile stress is the predominant failure mechanism for rock and chemical scale subjected to high-pressure jets. High-pressure water penetrates surface cracks creating local areas of tensile loading. Cyclical stress via pulsation of the jet, or rotation of the jetting tool, accelerates the rate of material removal. The standoff distance between nozzle and target is very important. The design of the nozzle profile will maximize the effective standoff distance and permit higher individual volume flow rates for the same pressure drop and ID. Tools with higher individual flow rates through a small number of nozzles are more effective than tools with smaller flow rates through a large number of nozzles, provided the entire target surface is covered during tool rotation. Additives are commonly used to make water more effective as a jetting medium. The use of long-chain polymer friction reducers, most commonly polyacrylamide, increases the effective standoff distance by reducing the tendency of the jet to diverge as it travels away from the nozzle. Also, very important in downhole applications, is the significant increase in pressure available at the nozzle as a result of reduced pressure drop due to friction along the coiled tubing. Let us talk about pre-packed GP screens. These are used through tubing gravel packing to repair failed GPs, install pre-packed screens through tubing after well has started to produce sand. Combination of pre-packed screen and gravel pack. Installation methods are washdown, squeeze pack, circulation pack. Washdown method. In this method, an improved well completion system for completing 2 or more separate production zones in a wellbore during a single downhole trip is disclosed. The improved completion system comprises a completion assembly comprising 2 or more production zone assemblies and a completion tool assembly. Each production zone assembly may comprise an automatic system locating assembly and at least 2 inverted seal systems for sealing against the tool assembly. Squeeze pack method. This involves cement being precisely spotted at the perforations. Additional pressure is then applied to dehydrate the cement slurry within the perforation tunnels in order to isolate selected perforated zones. Generally, this technique is not particularly successful for perforation isolation, a squeeze cementing method wherein the well tubing does not have to be pulled from the well so no workover rig is needed, a smaller volume of squeeze cement is required, the pressures involved in the squeeze operation can be precisely controlled with no risk of fracturing the formation, and there is no need for any drilling operations to remove hardened cement remaining in the well casing. More specifically, the present invention provides a squeeze cement operation that is carried out with a coiled tubing. The wellbore is isolated adjacent the perforations by flowing a packing fluid having a density greater than the cement through the coiled tubing to fill the lower part of the wellbore. An incompressible loading fluid is then flowed onto the packing liquid, and this is followed by pumping the squeeze cement down the coiled tubing. After the cement is placed, a contaminating liquid is flowed down the coiled tubing to mix with the cement left in the casing and prevent it from setting. The contaminated cement and packing liquids are then removed from the casing, which is then reperforated and returned to production. Bridge plugs. Wireline bridge plugs set on coiled tubing using a hydraulic setting tool. Retrievable inflatable BPs. CCL depth correlation. Pressure differential, a function of expansion ratio. The field-proven 3-piece packing element plugs the annulus. The bidirectional slips, which are caged to protect them as the plug is run into the well, enable the plug to hold pressure in both directions. The compact design also facilitates running into wells with high DLS. These bridge plugs equalize the pressure before releasing for retrieval, which eliminates the risk of trapped pressure pushing the work string out of the well. They can be retrieved with jointed pipe or fitted for retrieval on sand line or coiled tubing. Inflatable packers. They provide positive mechanical isolation. Depth control must be positive through either CCL, tubing end locator, tagging bottom, 3:1 inflate ratio, sensitive to BHT, limited amount of set/unsets. The inflatable packer is conveyed with coiled tubing into vertical, deviated or horizontal wellbores, eliminating expensive mobilizations and potential completion removals by enabling multiple treatments in a single intervention. The fiber optic real-time telemetry provides downhole measurements to optimize fluid placement, ensure accurate depth control, monitor packer pressure during setting and unsetting, and enable precise flow control and setting tool manipulations. During field testing, more than 147 inflation and deflation multi-setting procedures were performed. The active straddle inflatable packer was also field tested in more than 6 interventions in challenging onshore and offshore intervention conditions, including the Middle East and the North Sea. Now let us talk about data acquisition. It involves conveying logging tools, downhole sensors, and dead string during fracturing. Conveying logging tools. Deviated, horizontal holes. When pumping and logging is required. Its considerations are: wireline installation, depth control, tool compression, deployment. A method for conveying logging tools, or LT, and obtaining well log data from a wellbore is disclosed. The method includes running a drill string, or DS, including a landing sub, or LS, disposed near the lower end into a wellbore. A logging tool string, or LTS, is inserted into the upper end of the DS bore. A fluid is pumped into the upper end of the DS bore to assist movement of the LTS. As the fluid is pumped behind the LTS, the cable at the surface is spooled out and the fluid pressure is monitored. The landing assembly of the LTS is landed in the LS. A diagnostic test is activated and run to determine proper functioning of the LT. A release mechanism releases the running tool portion of the LTS. The cable is spooled in. The drill pipe string is pulled upward in the wellbore as the LT are recording data. Pumping during data acquisition. This encompasses pumping nitrogen to induce the well to flow during PLT. Pumping to cool down well during logging operations. Generating data during stimulation operations. The most common coiled tubing application is that of providing pumping services, such as tubing cleanouts and acid stimulation work, which eliminates the need for killing the well, bullheading, or contact of the live acid with the tubing string, etc. Nitrogen lifting is used to reduce the hydrostatic pressure of the column to induce production after a well closure or well intervention activity. Of particular importance in pumping applications is the pressure cycling effect on coiled tubing fatigue life, and the susceptibility of CT to collapse pressure. Now let us watch a visual illustration of a hybrid coiled tubing rig. Thank you for learning with us.